Okay, everybody, we're going to continue with Chapter 5, which is the reactions of alkenes and alkynes. And we're going to go into a number of skills that you're going to need to develop in this chapter. We're going to look at what the reaction is. We're going to look at how to predict products. We're going to look at what is called regiochemical and stereochemical outcomes of these various reactions. And then we're also going to look at reaction mechanisms. The mechanisms actually explain why certain products form or what type of regiochemistry and stereochemistry that you obtain. So again, instead of trying to memorize a whole bunch of facts, what you need to do is understand the chemistry, and then that is going to allow you to become proficient at predicting the product and looking at regiochemistry and stereochemistry and all of that kind of stuff. So let's get started. Okay. So these are the reactions of the alkanes or alkenes that we learned in this Chem 201 class. If you were to take Organic 1 or Organic 2, you would find this list to be just the tip of the iceberg. So if you go on to take Organic 1 and 2, at least you have done some of the fundamentals, which will serve you well when you go ahead and do the full semester class. If you're not going on, these are the ones that will introduce you to these reactions of alkenes. So the first reaction is called generically hydrohalogenation. So think of hydro meaning a hydrogen and halogen meaning my X. So basically I add an H and I add an X across the double bond. So an H goes here and an X goes here, and what I end up with is the H and the X, which in this top example is chlorine, right? And then the HX would be HCl, and I get the addition of hydrogen and the addition of halogen, which is why it's called hydrohalogenation. This works for the halogens chlorine, bromine, and iodine. You'll find that those are the three halogens that we use in organic chemistry. Fluorine is actually not used very much in organic chemistry because of certain properties of that second row element. Chlorine, bromine, and iodine are much more feasible in the types of organic reactions that we're actually going to discuss in this class. Now notice that this is called chlorination if the X is chlorine. That would also be hydrobromination or hydroionation if I change the X to another halogen. The next reaction is going to be hydration. Now, what do you think of hydration? You think of water. I'm going to break water apart though. And what I'm going to add is an H and an OH across the double bond. Together, that makes water, but I'm going to actually separate it. So I'm going to add an H and an OH to this double bond. And what I end up with is this alcohol. So I form an alcohol here when I do this hydration across the double bond. So see, I have the hydrogen to the one of the carbons and the OH from water at the other carbon, and I have added water across the double bond. The next one is going to be halogenation. Halogenation is X2, right? Which could be Br2, Cl2, or actually those are the ones that work the best for halogenation. So basically, I'm going to separate that out, and I add an X and then another X. So if it's Br, I add 2 bromines. If it's Cl2, I add 2 chlorines. So what you can see is one of the X's goes to each carbon. If the X is bromine, I get 2 bromines added. And again, this works the best for chlorination and bromination in organic chemistry. Now, if you notice, these guys, I have a top and a bottom. And in this generic structure that's drawn, that really doesn't have any significance. But when we actually go into that reaction, we will see that this diagram is going to refer to something called anti-addition, which we'll discuss later. This next one is called hydroboration. So I'm adding a hydrogen, and then I'm adding a BH2, which is from my borane starting material. So again, hydrogen is on one side and BH2 is on the other. The nice thing about this reaction is that I can actually do an oxidative process, and what I'm going to form is an alcohol. So I replace the Br2 with the OH in a second step. And I actually, this hydroboration oxidation mechanism or reaction is a great way to make alcohols. And this is going to have a different regiochemical outcome than this one. And we're going to be able to understand that based on the mechanism. The next one is just hydrogenation or reduction. Remember, a reduction is adding hydrogen. So my H2, I add 2 hydrogens, 1 to each carbon in my alkene, and I end up with an alkane as these 2 hydrogens are adding across the carbons in that carbon-carbon double bond. So this is an overview of everything that we're going to talk about and you are responsible for knowing these 5 reactions. And we will talk about regiochemistry, so you will have to predict the product. You will be responsible for regiochemistry, for stereochemistry, and the reaction mechanism for all of these different reactions. So let's continue on. Let's look at hydrohalogenation. So that's going to be HX. Here, I'm adding HBr or HCl to alkenes. What if I add HBr, I get an alkyl bromide. And if I add HCl, I get an alkyl chloride. And this is generally called hydrohalogenation. This is what it looks like. Here is HBr. I add across the carbons of the double bond. So notice that the hydrogen goes to one of the carbons of the double bond, and the bromine goes to the other. And I get an alkyl bromide. If I use HCl, that would be hydrochlorination. So this is hydrobromination. This is hydrochlorination. And the H and the Cl end up on each individual carbon. The hydrogen goes to one carbon of the original double bond, chlorine goes to the other carbon of the original double bond. So both of those carbons in the double bond get changed, and I go from this unsaturated to the saturated sp3 carbons during the course of this reaction. Okay, we're going to get into some terminology. The addition is regioselective. In a regioselective reaction, there are two different products that can be made. One direction of bond forming or bond breaking will occur in preference to all other possibilities. And if I can make two products by changing the carbons to which my atoms add and result in two products, one of those products is made in preference. So it's regioselective. Here's an example. This carbon is not the same as this carbon because this has two hydrogens and this has a methyl and one hydrogen attached to the carbon of the carbon double bond. So notice I get two different isomers. If the chlorine attaches to the red carbon, right? This is my red carbon. This is my orange carbon. When the hydrogen is attached to the red carbon, that produces, and you can name this 2-chloropropane. That produces one particular isomer from this reaction. Now let's look at the red carbon, and then I'm going to look at the orange carbon here. Notice that now the chlorine is on the orange carbon, and if I go ahead and I name this, I get 1-chloropropane. So basically, if I have this methyl group here, I can have the H and the Cl adding this way, or I can have the H and the Cl adding this way. So notice my chlorine can either be on this carbon or this carbon, and I just literally flipped the HCl around. Let me make that more specifically in H so you can see it in your notes, right? So if I call this A and I call this B, the product from A is indicated here, and the product from B is indicated there. I get these two different isomers potentially. What I see though is this one is actually not observed. And that's because of the mechanism of the reaction. This type of reaction, which is a hydrochlorination, actually observes Markovnikov's rules. The rule states, in additions of HX to a double bond, the hydrogen will add to the carbon with the greater number of hydrogens already bonded to it. And then the electrophile, the other part of the reagent, is going to bond to the other carbon. So notice another way you can state this is thems that haves gets. So notice if I look at this reaction again, this carbon has two hydrogens on it. This carbon has one hydrogen on it. So the hydrogen should go to that carbon. And when you do that, what you're going to get is the 2-chloro. You're going to get this isomer when that happens. So it follows Markovnikov's rule. The hydrogen in my HX reagent ends up on the carbon of the double bond that contains the most hydrogen. The halogen goes to the other carbon. And there's a reason for this that we're going to talk about. We will talk about this reason in the context of the chemical mechanism. So here's another statement of this. When I obey Markovnikov's rule, which is not general to this reaction, this is a rule that will apply to other reactions when I have an asymmetrical reagent. So when I have HX, when I have HOH, when I have HBH2, those are asymmetric reagents, and they may or may not follow Markovnikov's rule. This is the time when I have this asymmetric reagent that I have to analyze my stereo or my regiochemistry. So in the addition of HS to an alkene, the major product comes from when the H attaches to the double bond carbon that has the larger number of H atoms directly attached to it. The X attached to the other carbon. So again, here in this example, now I've added another methyl group. This carbon has 2 hydrogens attached to it. This carbon has no hydrogens attached to it. So my hydrogen should end up there, which means my bromine should end up on the other carbon. And that's what I see. This carbon is this carbon, and this ends up with the hydrogen. The other carbon, which is this carbon, ends up with the bromine. So the hydrogen attached to the carbon that has the most hydrogen in the starting material. The bromine ends up on the other carbon. If an alkene has equal numbers of hydrogen atoms, right? The 2 potential products that could be formed are formed in approximately equal amounts. So now I have, again, I have the red carbon and I have the orange carbon. This HBr could add this way, or it can add this way, right? So when it adds in the green way, this again is going to be my red carbon, and this is going to be my orange carbon. And when I form the bond in this direction, I get the hydrogen attaches to the red carbon and the bromine attaches to the orange carbon. If I do it the other way, here's the same red carbon that only has the methyl group on it, and here's the orange carbon that has the ethyl group on it, each one of these carbons only has one hydrogen. So this has one hydrogen and this has one hydrogen. The other substituent here is a methyl group. The other substituent here is an ethyl group. So they're not the same, which means that when I add in those two directions, I get two different products. When I do so in this direction, I'm going to get the hydrogen attached to the orange carbon and the bromine attached to the red carbon. And then, just like any other isomers, if I actually name them, I can clearly see that if I use IUPAC rules to name these, my double bond or my bromine is on either the 2 carbon or the 3 carbon, which means these are constitutional isomers. And it also means they're different products. So this alkene was asymmetric, right? I had one hydrogen and one methyl and one hydrogen and one ethyl. The difference with the methyl and the ethyl means that those carbons are different and I could get 2 potential products. But because each one has one hydrogen, neither of those 2 carbons has an extra hydrogen. They have an equivalent number of hydrogens. So both possible products are formed in relatively equal amounts. So I get a 1-to-1 ratio. There is really no rule to follow because these 2 carbons both have one hydrogen attached to them. So I get the 2 different products in that 1-to-1 ratio. And this is something you really want to consider when my double bond has got the same number of hydrogens, but has different alkyl groups attached to it, which gives it that asymmetry and makes the products constitutional isomers. All right, so let's try this. Complete these reactions by predicting the major product formed in each reaction. Now, I did mix things up a little because these 2 reactions are actually hydration reactions. And those 2 reactions also follow Markovnikov's rule. So hydrohalogenation and hydration follows Markovnikov's rule. So let's analyze what our reagent is. I have HBr, so the hydrogen is going to add to 1 part of the double bond, right? So here's my double bond. Those are the 2 carbons that are going to get some reaction. And I want to be able to tell which carbon of that carbon-carbon double bond does this hydrogen attach to. And there I'm going to use Markovnikov's rule for that. So when I look at it, this carbon has 1 hydrogen. This carbon has 0 hydrogens. So this is the carbon that the hydrogen should attach to. So this hydrogen should end up on that carbon. And do not confuse that arrow as an electron arrow, right? I'm just drawing connections at the moment. We'll look at the mechanism later. So all that arrow there means is that a hydrogen ends up on the carbon that has the 1 hydrogen and not on the carbon that has 0 hydrogens. So I'm going to draw this now in my product. So what I'm going to do is I'm also going to note then that if the hydrogen ends up there, the bromine will end up on that other carbon. So when I draw products, I basically redraw the structure because I have to draw every single atom that was in the original structure, and I have to draw what was added as well. So I'm going to have this CH3, CH, C, and then here I'm going to have CH3, CH2, CH2, CH3. So this is that propyl piece, and here's my ethyl. Now, what I've added is I've added a hydrogen to that carbon, and I've added a bromine to that carbon. So this is the major product. I could have added in the opposite direction, right? I could have had the bromine end up here and the hydrogen end up there. This would give me my minor product, which is the other isomer of this compound where the bromine is on this carbon and the hydrogen ends up on this carbon. So I always get those two potential regioisomers, those two potential constitutional isomers as my product. But according to Markovnikov rule, this is going to be my major product because the hydrogen ends up on the carbon of the double bond that has the most hydrogen, and then the bromine ends up on the other thing. Well, notice that this is also going to happen if my reagent is water. I have H and an OH. So again, this carbon has one hydrogen because it's the same identical substance. This carbon has 0 hydrogens. So I'm actually going to end up with this ending up on that carbon and this ending up on that carbon. So what I get is CH3, C, H, C, CH3, CH2, CH2, CH3, and then here I have my hydrogen and I have my OH. So again, the hydrogen ends up on the carbon with the most hydrogen and the OH ends up the other one. This is the major product. So I could get the other isomer from that as well, where I switch where the hydrogen would end up on this carbon and vice versa. But this is the major product. Oh, I wrote that already. The minor product is when the H is going to switch. I'm going to add the H to that one. Nope, that was the right one. I'm going to have OH and then H, where the OH ends here and the H ends up there. Try drawing those products as well. The key to drawing products is that everything else that's in the molecule stays the same. And I draw that out, and what I'm going to draw then is the changes for the reaction. So this is how I predict the product. This might be what you see on a test. Complete these reactions by predicting the major product. And I would predict the 2 products or the 4 products in these 4 reactions that are the major products. Those are the ones that end up following Markovnikov's rule. Here I have another example. I've got the carbon in the double bond. I have CH3, another carbon. I have a carbon and I have a hydrogen. So the hydrogen should end up here, right? Again, I'm adding H and OH. So when I think about that, I'm going to draw everything the way it is. This is the CH3. My H ends up there, and my OH ends up on this carbon. So this carbon is where my hydrogen or my oxygen adds, and then this carbon is where my hydrogen adds. And this would be the product, the major product. Here, I have another hydrohalogenation. Here's my alkene. This has 2 hydrogens on it. This has 1 hydrogen and a carbon. So my hydrogen is going to end up on that carbon. So I'm going to draw everything that I see. My hydrogen ends up here. And then my OH ends up there. And this is going to be my major product. Notice again that if I did it the other way and I ended up with the OH connected to that carbon and the hydrogen connected to that carbon, that would actually produce the minor isomer. If I see any of that, that's going to be minor. Okay, so we just finished predict the product with hydrohalogenation. The next part is going to take a little time, so I'm going to stop here, and then when we return, we're going to consider the mechanism of hydrohalogenation. The mechanism of hydrohalogenation is going to explain why I get Markovnikov's problem, or Markovnikov's addition, in terms of my regiochemistry. So that is the end for today. I will be back. I mean, not for today, but for this part.